This short video is designed to explain how some of the more complex collective variables that are available in PLUMED work. You can use a very wide range of collective variables with the features that are already available in the code. However, finding out how to do these calculations can be difficult if you don't understand the spirit in which the code was written. One of the most common questions we are asked on the PLUMED mail list is, what collective variables should I use? Sadly, this is not a question we are always able to answer. The plain fact is that collective variables are a tool for understanding simulation data, and when deciding what variable to use, you need to think carefully about the sort of questions you want to answer and about the particular system you are studying. Different problems will require you to use different variables and different methods. What, you then may ask, is the point of PLUMED? Well, our hope is that once you have thought of an appropriate variable, you will find that there is an implementation of that variable in PLUMED, and that you can thus get your simulations up and running relatively quickly. At the same time, though, we don't want PLUMED to expand to be an enormous and unmaintainable code. And we also want to minimize the amount of input syntax that you have to learn. With all this in mind, let's think about a relatively complex variable that has been widely used in free energy simulations, the coordination number. Let's suppose that we want to calculate the coordination number of the red atoms shown here with all the blue atoms. To calculate this quantity, we first have to calculate the distances between the red atom and each of the blue atoms in turn. We then introduce a cutoff and calculate the number of distances that are less than this cutoff. In practice, so that we have a differentiable coordination number, this is done by transforming each of the distances by a monotonic decreasing and continuous function that is one when the distance is less than the cutoff and which goes smoothly to zero outside this cutoff distance. Mathematically, we can express this calculation as shown. In this formula, bold X is the positions of all the atoms. Each of the Fi of x functions is one of the distances. Lastly, g is the smooth cutoff function. Writing the expression for the coordination in this abstract notation reveals something. We are doing very similar operations when we calculate a wide variety of different collective variables. In fact, all we need to change to calculate other things are the Fi functions in the expression and the way that these base functions are transformed, that is to say, the function g. As an example, we could sum over angles rather than distances and transform each angle by dividing by the total number of angles that we are calculating. This would give us the average angle using a very similar formula to that used to calculate the coordination number. What this means for PLUMED is that we can use the same code to perform a wide variety of different calculations and thus ensure that much of the code is parallelized and fast. What it means for users is that you should think about the sort of variables that can be computed in a slightly different way. Recall the abstract equation that we defined by considering the coordination number. An alternative way we can think about this equation is to think that when we calculate a large number of quantities from the positions of the atoms, we have a probability distribution for the various f values. So, if each fi function is calculating a distance, we have a probability distribution for the distances. Alternatively, if each fi function is calculating an angle, we have a probability distribution function for the angles. Whenever we have a probability distribution, and it looks like the one shown here, a sensible thing to calculate is the mean. Alternatively, we can calculate the variance of the distribution. In fact, we can calculate any one of the central moments of the distribution of base variables. For many quantities, this approach is not ideal, as we often find that the distribution of base variables is multimodal, like the distribution shown here. For these kinds of distributions, it is often better to calculate the number of base variables that are less than a certain target value, or the number of base variables that are larger than a certain target value. Alternatively, you could calculate the number of base quantities that are within a certain range. This sort of thinking is the basis of the multicolvars that are part of PLUMED. Each of these commands can be used to calculate a variety of different collective variables, and so you should look carefully at what each of them is capable of whenever you want to perform a calculation with an unusual variable. You may well find that the variable you desire is implemented in PLUMED, but that it is hidden in a multicolvar. Let's have a look at how multicolvars are used in practice. The command shown here tells PLUMED that the base quantities that it is calculated are the 6 distances between the atoms shown in the above figure. As you can see, each base quantity, each distance, that must be calculated is specified by using an atoms keyword, which is then followed by the 2 atoms that should be used in the calculation of this distance. As with any command that reads in atoms, in PLUMED, these atoms can be specified using their numerical index of the MD code's input file, or by using a virtual atom position such as a centre of mass. Writing out the atoms involved in each distance manually would become rather tedious if a large number of distances were required, so we also provide a shortcut. You can provide 2 groups of atoms using the group A and group B keyword, and PLUMED will know that by this you mean take every distance that can be constructed by taking 1 atom from group A and 1 atom from group B. The rest of this distances command tells PLUMED that what is desired is the minimum from amongst the set of distances that have been computed. Note that the minimum has to be calculated by transforming each of the distances by a function, g, that is differentiable. This is the reason for the additional parameter beta. In this PLUMED command, the minimum distance is being output to a file using the print command. To do this, we have to reference what from the command label D1, the distances command, should be printed out. For obvious reasons, the quantity we desire, the minimum distance, is labelled d1.min. We can change what quantity is calculated by distances as shown here. Now we are calculating the number of distances that are less than 1 and printing it to the colvar file. It is important to note that there is nothing stopping us from counting both the minimum distance and the number of distances less than 1 at the same time. This can be done using the input shown here. If we could only do this with distances, the multicolvar feature would not be very useful. The advantage of this new feature in PLUMED is that we can use a similar syntax with a wide variety of different base variables. For example, on this slide, we are working with angles. Here, the groups are used to specify that we should calculate angles around atom 1 that involve 2 of the atoms from the second group, the atoms 2 to 8. The between keyword then tells PLUMED to calculate the number of these angles that are between pi by 4 and pi by 3. The switch command here is optional. Without it, we would consider all possible angles. When it is present, however, we only consider those angles involving pairs of blue atoms that are both within a certain cutoff distance of the red atoms. We can thus use the angles command together with the switch keyword to calculate functions of the distribution of atoms in the first coordination sphere of the central atom. A third example of where multicolvars can be useful is when you are calculating symmetry function. A symmetry function measures how atoms are distributed in the coordination sphere around a central atom. The simplest one of these is the coordination number, which measures the number of atoms in the first coordination sphere. The command shown here tells PLUMED to calculate the coordination numbers of the 2 red atoms with the blue atoms. The number of coordination numbers that are more than 4 is then computed. In this example, the user has assumed there is something that distinguishes the red atoms from the blue atoms. If there is no such thing, then you may just wish to calculate the coordination numbers between each of the blue atoms and all the remaining blue atoms. This can be done by changing the command as shown. A nice feature of symmetry functions is that, because they are generally atom-centered, we can calculate the average value of the symmetry functions in a particular part of the cell box. In PLUMED, this is done using the around action. When using this action, you have to ensure that the variable is invariant with respect to a global translation of all the atoms in the box. As such, the reason of interest has to be defined with respect to a particular atom. In the example shown in the slide, this reference point is the position of the centre of mass of all the atoms in the system, C1. As shown in the figure, once this reference position is defined, one can calculate the average by adding together the coordination numbers of the 6 atoms whose x-coordinates are within 0.3 nanometers of the reference x position. Notice also that the around action behaves like a multicolvar, so you could also use it to calculate the number of atoms in a part of a box that have a coordination number less than 4, a coordination number more than 4, the minimum coordination number in a part of the box, and so on. If you are studying crystallization, there are a whole separate set of functionalities that you can use that are based on this multicolvar notions. These functionalities are the subject of a separate video, however. You can find this information on the PLUMED website, as well as a great deal of information on all the functionalities that are available in PLUMED. Thank you for your attention.